With the recurrent neural network layers that you've used so far, the layers have only returned the output at the final time step, which you've then used to pass through to a final output layer to make a prediction. But this isn't always how you'd like to use recurrent neural network layers. Sometimes what you'd like is for a recurrent layer to return an output at every time step in the sequence. These outputs can then be used for the final model predictions, or could be used as an input for another recurrent layer further downstream. In this video, we'll look at some different ways of incorporating recurrent neural network layers into your model, including returning sequences of outputs and also bidirectional recurrent layers. Here's a reminder of how a recurrent neural network layer can be included in your model. This time we're using the functional API. We're defining the input layer to have a shape of none by 10, which means we have a flexible sequence length and there are 10 features per time step. Remember, this means the model is expecting an input that is a three-dimensional tensor with the batch size in the first dimension, the sequence length in the second, and the number of features, 10, in the last dimension. We've then got a masking layer to handle the padding in the inputs, and we're telling the model that the padding value that has been used in the inputs is 0. The masking layer here ensures that the network will ignore any parts of the sequence inputs that are just 0 padding. This is then followed by an LSTM layer with 64 units, and the final state of that layer is passed through to a dense layer with a 5-way softmax. Let's take a quick look at the tensor shapes after each layer. As we mentioned, the input layer has been set up to have a flexible length input, so the shape is none for the batch size, none for the sequence length, and 10 for the number of features per time step. The masking layer doesn't change the shape of the incoming tensor at all, it just creates the Keras mask by looking for the 0 padding values in the input. The LSTM layer only emits the output at the final time step and has 64 units, so the tensor shape for the output is none for the batch size, and 64 is the number of units or features. This is then processed by the dense layer, which has just 5 units with the softmax activation. Each of the recurrent neural network layers have an optional keyword argument to return sequences. This is false by default, which is why the layer only returns the output at the final time step. But if this option is set to true, then the layer will return an output for each time step. So this is how the tensor shapes would look like now after each layer. Notice that the shape of the output after the first LSTM layer is still a three-dimensional tensor of the form batch size by sequence length by features. This of course can be used as an input to another recurrent neural network layer, and that's what we're doing here. The following LSTM layer has return sequences set to false, so again only returns the final output, and so the tensor shape becomes none by 64, none for the batch size, and 64 for the number of units in the LSTM. This is how we can create stacked LSTMs. The return sequences equals true argument means that the output retains the sequence dimension, which can then be passed into another recurrent layer for further processing. I'd also like to introduce one more thing that is often really useful in recurrent neural network models. Bidirectional recurrent layers are often used when we like the network to take account of future context as well as past context. In TensorFlow, we can create a bidirectional layer by using the bidirectional wrapper and calling it on a regular recurrent layer. Here we can see how this works. I'm importing the bidirectional layer from tensorflow.keras.layers as usual. In this line, you can see how easy it is to create a bidirectional layer. All I'm doing is taking the LSTM layer and passing it into the bidirectional wrapper. In this recurrent layer, the LSTM has return sequences equals true, and so this will mean that the bidirectional wrapper will also return sequences. However, we can also use the bidirectional wrapper on recurrent layers that have return sequences set to false. That's what we have here in the second recurrent layer, since return sequences is false by default. Remember that with return sequences set to false, the output of the layer is the output at the final time step, But because this is now a bidirectional layer, we effectively have two LSTM networks, one running in forwards time and one in backwards time. So the output will be a combination of the final outputs from each of those recurrent networks. So again, let's just think about what the shapes look like for each layer output. The first bidirectional recurrent layer returns sequences, and because it's bidirectional, we have two LSTMs running in each time direction, and each of these has 32 units. That means that the output of this layer will have a tensor shape, none by 64. The first dimension is the batch size, as always. The second dimension is the sequence length, which in this model is flexible. And the feature dimension is the concatenation of the outputs for each of these LSTMs running in forwards and backwards time. Each LSTM has 32 units, so the layer output will have 64 features. The next bidirectional layer has return sequences set to false, and the LSTM instance we're calling it on has 64 units. So again, we can think of there as being two LSTM networks, one running in forwards time and one running in backwards time, and the final output of each of these networks is concatenated to make a tensor with shape none by 128. We can also change the behavior of the bidirectional wrapper. As we've seen, by default, this wrapper concatenates the outputs of the forward and backward RNNs. We can change this with the merge mode option. The default value for this argument is concat, but if we set it to sum, then the forward and backward RNN outputs will be added together instead of concatenated. In this example, I've set the merge mode to be sum in the first bidirectional recurrent layer, which means that the output tensor shape will change. The tensor shape of the output is now none by 32, as the 32-dimensional outputs of each LSTM will be added together. You've now seen how to build flexible and powerful recurrent neural network architectures in TensorFlow, and how easy it is to build these networks with both the sequential and the functional API. In the final coding tutorial of this week, Jerome will walk you through using these layers to create stacked RNN models with bidirectional recurrent layers on the IMDb dataset.